presentation will be given by Professor Mário Ernesto from Federal University of Sergipe with the work entitled, Can We Understand the Transit Dynamics of Charged Carriers After X-ray and or VUV UV light excitation?
Hello, can all you hear me? Okay, so now I have to share my screen. Okay. Is that okay? Good. So we are now changing completely the gears. We're moving to the other side of the electromagnetic spectrum. In our case, we are interested on scintillators and the mechanisms that drives the properties. So as I will tell in a few minutes, what's a scintillator, and also it's not an experimental, although I am an experimentalist, but we're dealing with modeling. Because in our group, we treat scintillators, we prepare some scintillators, some detectors, so we want to understand better how the behavior of the scintillator is. And one important aspect of a scintillator, if the mouse let me do that. Yes. So what is a scintillator? A scintillator is basically an energy converter. You shine ionizing radiation, the material, and it converts on light. And you use the light to detect the amount or do whatever you need with the information that comes from the ionizing radiation. And one key aspect that drives all the main properties of a scintillator is the dynamics of the charge carriers that are generated inside of the material as a result of the ionizing radiation. And the ionizing radiation here can be from electromagnetic to particles, charged particles, anything that nucleons, neutrons, anything that generates charge carriers in the material. And these charge carriers will have a kind of dynamics that depends very much on the material itself, and that defines how the light is produced, the intensity and the time duration of the light. And that is the thing that we want to understand a little bit better. So scintillators can be used in a variety of things. There are a lot of applications, like if you go into an airport. I flew from Aracaju and I went through the airport, so they have the X-ray machine there, where they have a big scintillator screen to screen the baggage and see what you have inside. So it goes from that application to medical applications and radiation in physics. In the CERN lab, they have tons of scintillators that are used to detect the particles. So scintillators are a very diverse application range, and this means that you also need materials that can cover different aspects, different type of radiation, and also in different time scales. And that's important. That's a key issue, is why we still have jobs, because you need to develop new scintillators better, and so on and so forth. So here you can see an example of a scintillator having the X-ray on and the light shining, and that's the important thing. So the important thing is here is the scintillator material is normally part of a kind of device. You have the X-ray that reads the scintillator, and then you have the UV detection the light detection, and then you get the electrical signal. So the important thing that happens in this first layer is that where the scintillator itself is the energy converter itself is located. So it's a very important, and we have a lot of different steps that happens after the radiation is received by the scintillator. The first step we divide that as a kind of is a way of separating all the process, but actually it all happens in kind of simultaneously. The first step is the energy conversion into electron hole pairs. So the energy is received by the material, and you have a number of electron hole pairs that are created, primary created. Then we have all the thermalization process of the electron hole pairs, because you create them with quite high kinetic energy inside of the material. There's a lot of process that happens, like scattering, elastic scattering, so on and so forth. And then you end up with the electron holes on the top of the tube, on the bottom of the conduction band and the top of the valence band. So this is what we call thermalization. Then you have the energy charge transfer to the luminescence center. It means in some way this charge has to transfer the energy to whatever the light is going to be generated. There we have a lot of different possible mechanisms. I'm not going to go into too much details that, but just going to give some few examples. And then we have the light emission itself. So all this process, they can be kind of ranked in a kind of time scale, and I just summarize them here. It can go from 10 to minus 9 nanoseconds up to centuries. Because sometimes the energy is storage in the material, and you have to do something to recover that energy back. And if you just leave the material there, it can storage that history for centuries. And that is very important because this is used in dating, in different dating process like geological or archaeological date. They use this as a kind of retrieving the prehistory where we have the radiation done. So we have a very huge time scale. And the question is how all these dynamics of the charge carriers impact on the properties. So we can have things that, like this, you switch on the X-ray and then the light starts increasing steadily and you can stay there for hours and the light yield keeps increasing. We can have properties, the light intensity depends on temperature of the detector. You can have the same samples that you change the luminescence center and you have different time profiles, and so on and so forth. So this is the question that we decided to deal with. And how these are treated in the literature. In the literature, there are some analytical models where we need to do a lot of very, very specific, and we have to do a lot of approximations. We have some empirical model, and that is very common. I just get one of the signal and say, okay, this looks like an exponential decay, and just fit with as many exponential decays as I want, no matter if there are any physical meaning or not. Anyway, I get some numbers that are important for building the devices, because they need, someone that is building the device needs to know how many time or what is the length, the typical length of time between receiving the photon and getting the light out. And when this light is faded, that you can consider that you have a separate pulse. So that's a very specific application for. So these empirical models work okay. There are some other empirical models that is based on, I like this kind of things and I don't like that, so I am going to use this. It's very common in the literature to find that. Actually, the main books about scintillators says normally say that the exponential decay models are used without any specific or any proof that is really what happens. And there are some cases that we don't have any model at all, like this one is very difficult to explain how this behavior happens in the material. So our task is to try to find a way of model all these kind of things. And so what are the ingredients of our model, of our cake? And what is the recipe that we are going to be using? So first of all, what we are going to do is we are going to be using one thing that's very common in the luminescence community since Becquerel, or radiation, since Becquerel, that is using rate equations. That means that the amount of decay is a relative, it depends on a certain constant. So the decay, the number, the percentage number of species that decays from the excited state to the ground states depend on a constant and the length of time. And so in that way, each process has a characteristic probability and constant. So this is a typical application for that for luminescence centers, where the intensity of light is proportional to the rate of change of the excited state population. And then they have a specific time constant that we call the characteristic time of the material. And that is used to characterize, and when we say, for instance, a scintillator has a characteristic time very short, that is the number that we are talking about. But what about, okay, I can do that for the luminescence part. But what happens to before the luminescence being excited? There's a whole bunch of other things that happens in the material before the luminescence center actually gets the energy enough to be excited. So then we need to work out all the dynamics of the charge carriers. And then what we are proposing is to do it quite simply. We have two main processes, that is exciting, generating the electron hole pairs. And then these have a probabilities that basically experimental probabilities, depends on the radiation pumping that you're using. And then there is a process here that involves both thermalization and recombination that gives the energy out of the primary process that is creating the electron hole pairs. This will be characterized in our model by alpha, and the typical times here are it can range from 10 to minus 5 to 10 to 1 nanoseconds in a typical scintillator. And the process that we call zero, that is the starting of the whole thing, is a function that depends on how I'm pumping. So the idea is that I can model the pumping and let the system evolve and see what happens. That is the basic things of the process. So what about the results? Now I'll show you two simple examples. What we have been doing other examples, it does not only are devoted to these ones. But the first one, we have one luminescence center and one electron hole pairs creation and recombination. It means that I am combining the luminescence emission with, I'm putting the luminescence center inside of a material, typically a crystalline material, is a scintillator normally. For the type of application we're thinking about, it's a crystalline material, so we have the band gap, the energy gap, and so on and so forth. And then we have the other two processes that we have already discussed. And now we are going to coupling all these things in a kind of nice story from the very beginning to the light coming out from the material. So if you look to the dynamics of the electron hole pairs, so the rate of changing in the electrons, N means the concentration of electrons in the conduction band, and H, the concentration of holes in the valence band. So both dynamics depend on two main processes. Alpha is creating, so alpha increases the number of pairs, And this other process is that the recombination has a minus signal because it decreases the amount of concentration. So it's a combination of these two that defines the dynamics of the electrons and holes in the system. Our materials are normally neutral. The nature always find a way to neutralize itself in terms of charge. So we are starting from the charge neutrality, and typical values from this alpha depends on the pumping, and gamma depends on the pumping scheme. We are simulating two types of pumping, and alpha, as I showed before, depending on some values found in the literature. As for the luminescence center, we can say, okay, I can apply the same equations for the intensity of the luminescence center. But if you say that the intensity depends on the rate of change of the concentration of the luminescence center, is not true anymore, because the concentration of the luminescence center now has two parts. One is the excitation, is when the electron hole pair recombines itself and transfer to the luminescence center, so you increase the population of the excited states. And the second part is actually the luminescence center emitting the photon coming back to the ground state. So the luminescence is actually only related to this part, is that the emission part. So we no longer has the intensity proportional to the rate of change of the luminescence in excited state, but actually depending only on one leg of the process, and this couples all the process inside of the material. So in the excitation, we are going to have a look in close to these two terms. This is the energy transfer to the luminescence center via recombination. It depends on the process itself and the efficiency. This number is very, very difficult to figure out. So in our model, we still fix it in one, because the efficiency of the transference process is almost impossible to detect. And the second term is actually the concentration of available luminescence centers in the material, because we are working with a system that has a limited concentration of luminescence center. This is what happens in the nature. Depending on the dose in the material, can saturate all the luminescence center, and then there is no way on putting more dose, because you already saturate, you're not getting any light out unless you increase the concentration of luminescence center. So it's a limiting, so it's an important factor here. So now we have a system of differential equations that can be solved, has to be solved, and what we did is just solve it numerically using a simple program in Python. I think most of the students here will know, use the SciPy library. They have a way of solving differential equations. You just plug the things there, and then we start getting quite interesting results. So the first experiment we did, I forgot to see how many times I still have. 6? Okay, so I'm just gonna show this example. So the first experiment we did is we simulate an X-ray pulse. How we did that? In the lab, in the real life, we know that a pulse has a time duration. But in our case, what we did, we admit that the pulse is a kind of delta. So instantaneously, we have no concentration, and in T equals 0, we have a certain concentration of electron hole pairs in the material. So that's the way that we simulate the X-ray short pulse, and then we expect to get something like that. This is one of our experimental results. So the first result is if we increase, here is the effect of the concentration of luminescence center. What I have here is what is expected. We have a straight line that basically depends on the time constant of the luminescence center itself. And as you increase the concentration, you have the amount of light increasing with with that. So no big deal concerning that one. But then when we start playing with other figures like the recombination rate, then things start showing a little bit some interesting results. Let me just put here. The alpha constant is increasing, moving down in this figure. So when I have a very strong recombination rate, it behaves like if I just have the energy immediately being transferred to the luminescence. But if this process starts being slowed down, it means that the luminescence centers start taking longer to be excited. Then we have a kind of deviation from the exponential model, although the luminescence center itself has, in all cases, the same time constant. So I'm not playing around with the time constant. I'm not including any other luminescence centers, just the effect of the recombination rate. It's quite interesting. So I'm just going to show you when I have trapping, I can include an extra process that's very common. When I have a defect in the band gap of the material that can trap the charge, either the electrons or the holes, is very common in any kind of material. What happens in these cases? And then we have to play around with other set of equations here. We have the concentration of electrons in the traps, and so we have a different equation for the charge neutrality. Now I have to have all the electrons have to sum up to being equal to the holes, and then I have another different dynamics because now I have three different processes that plays with the concentration of electrons in the conduction band. So we have this recombination, the trapping and the detrapping of electrons, and then this changes a lot. And if you, I'm just going to skip this one just to show the same experiment because I'm running out of time. So if we do the same experiment like the simulated X-ray pulse, again, doing the same thing, if I just choose one of the curves that I have no trapping, the P parameter is the trapping. So I'm just simulating the situation as before. But as soon as I increase the trapping, then a lot of different things starts happening. And again, here is a variation of the recombination rate. Again, the recombination rate is is increasing when we move down here. And again, when we have a very high recombination rate, the curve lies on the single exponential decay. But as soon as I decrease the recombination rate, these curves start moving up and even making funny things in the main process. If I pick one of that curves, I can easily mistake that by two exponential model. I just get one of that curves and fit it to sum of two exponentials. And that fits reasonably well. So the question is that really what is happening in the material? This is one of the results in the literature. And I can say that because that's our results. And we have done that. Because by that time, we didn't have a better explanation. But we can ask, is that really a two centers? Did I really have two luminescence center that has two characteristic time? Or this is an effect of slowing down of the recombination because now I have a trapping combined with different recombination probability. And if we collect one of that curves that we generated there, it actually resembles our curve, our experimental curve in the very beginning here. Remember, t equals 0 is when I switch on, when we switch off the X-ray. So when we switch off the X-ray, the light is still coming up and then it starts going down. So this is an effect of trapping plus slowing down the recombination process. That can be a possibility, okay? So we have a lot of other results. Here we have a result that we can simulate the effect of temperature. If we decrease the temperature, that's very common in a scintillator detector. We decrease the temperature because then we increase the signal to noise ratio. It is better to measure, but actually what we can do is that we can ruin the system because at low temperature, at the room temperature, the detector is fast because the trapping is not playing too much importance. But when I freeze or I decrease the temperature to like 8 Kelvin, then I start stabilizing some traps that slow down the whole process and ruins the time characteristic of the detector. So this is just a few things that we did. Let me just move straight to the conclusions. Okay, so can we understand, was the main question that we proposed, can we understand the transient dynamics and what happens with the charge carriers after X-ray or VUV? Yes, I think we now have a tool that can be used too. There's a good chance that we can, if we consider carefully all the process that may be happening inside of my material. So the question that we have to ask is, what kind of material I have, what I know about the material, what are the processes that I may have there, and with that, we can start building up a model and see what will be the dynamics and try to understand, and even playing around to increase or to make a better detector by knowing that. Dynamic of charge carriers is very important feature. It can be easily mistaken by like different luminescence center, but it's actually just a matter of the dynamics of the charge generated, nothing really related to the luminescence center itself. And rate equation is a crude approximation, but it's treatable and can give us some light and can give us, to make a joke, can give us some light and can help us understand what's going on. And with that, I want to thank again for you all and to our group in our university. Thank you very much.
Thank you, Professor Mário. We have time for questions. Any questions? Professor Mário,
either everything is so clear or so confusing.
It was very clear. Can you take in consideration the reabsorption process?
Yes.
Of the luminescence center?
Yes, it is possible. We actually, it's very dangerous to say this, what I'm going to say now. We can do whatever you want. It's just a matter of figuring out what's going to be the process and working out the constants and dynamics. The problem is that when we start increasing the number of things, one of these very known researchers once said, give me an equation with 25 parameters and I will fit an elephant running. So that's one problem, that it has to make sense. So if we have information from the material, from some other techniques, from some other inspection, from some knowledge that we have, that this is actually happening, can we? Yes, we can. And see how that will impact on the whole property of the material. Yes, it's possible. It's possible and it's feasible. Just a matter of adding some more terms and one extra differential equation to the process and solving altogether. It's not a big deal. The problem is this has some physical meaning. That's the important aspect that we have to think always.
More questions? Okay.
Hi, thanks for the nice talk. I
Thank
think
you
it
very
was
much.
very clear instead of very confusing.
Thank you.
But I just have a doubt. I wonder if there are any. You mentioned that you model the detector material as a semiconductor, right? Having a band gap, a conduction band and a valence band. Are there any detectors, scintillators, detectors made of different materials that are not semiconductors that it can kind of
Actually, the scintillators, the inorganic and solid scintillators are separated in two big classes. One is glasses, and the other one are crystalline materials. Within the crystallines, you have you have inorganic. That's most of the scintillators using, like in baggage inspections or in the detectors in physics, are inorganic, so it's a kind of wide band gap materials. And we also have semiconductors, like silicon-based, germanium-based, that has a different kind of application. These ones, the semiconductors, are used more for analysis of the energy spectrum of the radiation to determine what kind of radiation you have. If you have like a bunch of radioisotopes, what are the radioisotopes? Because you have the spectral response in terms of the impinging gamma or X-ray energy that arrives in the scintillator. So the inorganic one is really the big market for tomography, inspections, luggage inspections, detectors in Large Hadron Collider. They have huge tons of crystals about this size, this diameter, big, like something like 100,000 per detector. It's really amazing. But they are mainly inorganic ones. So this model of having a band gap is quite feasible.
Okay, thank you. Let's thank speaker again.
Thank you very much.
Now we have a virtual presentation